In this video, we're going to use a triple integral to figure out the volume of a solid. So we want to find the volume of the solid enclosed by the paraboloids y equals x squared plus z squared and y equals x minus x squared, y equals 8 minus x squared minus z squared. So both of these paraboloids will go along the y-axis, if you will. The y-axis will be running right through the center of each paraboloid. One is kind of opening, if you will, in the positive y direction. That's the y equals x squared plus z squared. The other one's opening in the opposite direction. So it's probably easiest to integrate with respect to y first on the inside, because I see that my y is bounded by the x squared plus z squared below and the 8 minus x squared minus z squared above. So we'll describe our y's in terms of those two particular surfaces as in between those two things. Now we see that our intersection of these two surfaces is the circle x squared plus y squared equals 4. If we imagine taking this and smashing it down to the xz plane, that means our x and z have to satisfy the inequality x squared plus z squared is less than or equal to 4. So I can rewrite this in terms of solving it, say, for a z, and getting the z has to be between the negative of square root of 4 minus x squared and the positive square root of 4 minus x squared, and then your x rows run from negative 2 to 2. That's one way to describe that particular disk. Alright, since we're trying to find the volume of the solid, we know that we can get the volume if we just integrate 1 dy dz dx. So that's why we're just doing the triple integral here and not having any other function besides the constant function 1 here. So obviously an antiderivative for 1 is just y, and then we can plug in our endpoints, and we just end up with the difference of the endpoints, which will just be 8 minus 2 times the quantity x squared plus z squared. Alright, we can certainly go ahead and do this integral if we really, really wanted to. But at this point, we notice a couple of things. First, I notice I have an x squared plus z squared. Second, I notice that I've described a circle that we're doing our double integral over. That's a lot easier to describe in polar coordinates than it is in rectangular coordinates. I can describe this circular disk that we're integrating over as the r has to go between 0 and 2, because the radius is going out from the origin out to an edge point, which will have a distance of 2 from the origin. And then we can rotate around 0 to 2 pi to trace out the entire disk. So when we convert it to polar, we'll just be integrating 8 minus 2r squared, 0 to 2 for the r's, 0 to 2 pi for the thetas, and then remember when we replace the dx dz in this case, that extra coefficient of r, that extra factor of r pops out. So we get the r dr d theta when we replace the differential. Now I've got function of r with no thetas, so I can actually split this into a product of two integrals. I can do the integral with respect to r times the integral with respect to theta, because this is constants for both of our sets of limits of integration, and I can split my integrand into function of r no thetas times function of theta no r's. Integral from 0 to 2 pi of d theta is just 2 pi. Here we can get an antiderivative for our r's, plug in our endpoints, and end up with a final answer of 16 pi.